This transformer steps down the 120 volt AC to 5 volt AC. It's called a split bobbin transformer because both the primary and secondary windings are spun around separate bobbins that resemble sewing bobbins. The secondary windings are on top of the primary windings, but physically isolated from each other. According to Faraday's law, an alternating magnetic field in the primary windings will induce an alternating voltage in the secondary windings. That's how power is transferred from the primary to the secondary. The steel core is an excellent conductor of magnetic flux and concentrates the flux for maximum coupling between primary and secondary windings. The steel core is also an electrical conductor, and an alternating magnetic field induces electrical currents called eddy currents within the core. These eddy currents cause the core to heat up. This core is constructed using laminated steel sheets that reduce eddy current losses so the transformer runs cooler. I'm putting channel 1 of my scope across the 120 volt AC hot and neutral. That's the primary windings. And I'm putting channel 2 across the secondary 5 volt AC output. As you can see, the voltage is stepped down from 120 volt to 5 volt. That's a turns ratio of 24 to 1. If my residential voltage was low, say 110 volt AC, the transformer output would only be 4.5 volt AC. The transformer output is rated at 5 volt, but that's assuming a perfect 120 volt AC input, and it's also assuming a perfect load. The perfect load resistor is one that draws the maximum current, that's 400 milliamps or 0.4 amps. Using Ohm's law, the load resistor should be 12.5 ohms. Using the power equation, the load resistor needs to handle at least 2 watts. An easy-to-find full load resistor is 10 ohms at 10 watts. It's big and chunky and flame retardant. Here's a Class 2 power supply. That means that the secondary is low voltage, that it's low power, and the primary and secondary windings are physically separated, like in a split bobbin transformer. Class 2 also means that the adapter doesn't need the third grounding prong, and the 2 outlet prongs don't need to be polarized. The AC adapter can be plugged in either way. Here are 2 logos, the UL listing and the CSA. The UL stands for Underwriters Laboratories, and CSA is Canadian Standards Association. These organizations test and certify that products meet published electrical safety standards and electrical code. Their main concerns are hazards like electrical shock and fire. If there's an internal short within the AC adapter, then touching the adapter will not be an electrocution hazard, and the adapter will not heat up and catch fire, nor get so hot that it burns you when trying to unplug a defective adapter. The split bobbin transformer is an isolation transformer. The secondary windings are isolated from ground. Here's what that means. The 120 volt AC residential electricity on the primary is referenced to ground. If you're unfortunate enough to touch a live wire, deadly AC will seek ground through your body and you will receive a terrible shock or get electrocuted. However, touch either secondary leg and you won't feel a thing. That's because the secondary does not seek ground as a return. The return is from one secondary leg to the other. To receive a shock, you'd have to touch both secondaries at the same time. Now grab the secondary leg and a good ground and you'll feel a trickle current. That's because there's a tiny AC current that passes from primary to secondary via capacitive coupling between the primary and secondary windings. going to back engineer this AC power adapter. It's got a step-down transformer, a bridge rectifier, a filter capacitor, and a bleeder resistor. I'm putting channel 1 of my scope across the transformer secondary. It's a 32-volt peak-to-peak AC sine wave, and that's under no load. I'm putting channel 2 across the bridge rectifier, which converts the secondary AC into a pulsating DC voltage. During the positive half of the AC input wave, these two diodes that conduct. This is positive and this side is negative. The plus comes up here, forward biases this diode, and here we get the plus side. The minus goes over here, forward biases this diode, and that goes to ground. Now for the bottom side of the AC cycle, these two diodes are conducting, and here we have the minus side up here and the plus over here. Now the plus comes up over here, forward biases this diode, and we get the plus side. The minus comes over here, forward biases this diode, and that goes to ground. On the positive side, this is the pulse that comes out of the bridge rectifier. And on the negative swing, we get this positive pulse. The pulsating rectifier output goes from ground to 16 volts peak, minus the 0.7 voltage drop across each diode. So the peak voltage will be 14.6 volts. Now I'll add the filter capacitor, and that will smooth the pulsating DC into a constant DC voltage. To understand how the filter capacitor does its job, we'll need to take a look at the charging current, so I'll add the current probe right here. After a few AC cycles, the capacitor charges to about 14 volts. Here the voltage rises and rises until you get to about 14.6 volts. At that point, this diode forward biases and we get a spike of charging current. When it gets to about 14 volts, that diode reverse biases itself, and then the voltage falls back to 0. Now we're going to enter the negative part of the AC cycle. Once again, the voltage rises. When it gets to about 14.6 volts, the other diode turns on and conducts. And then when it gets to 14 volts, it too reverse biases itself. And then it goes back down to 0. And this cycle continues. And this is how you get the ripple voltage on top of the DC. This adapter has a bleeder resistor. When the adapter is unplugged from the wall outlet, the capacitor retains its voltage. The bleeder will discharge the capacitor and prevent the spark, sometimes seen at the barrel plug. I've unplugged this adapter and the capacitor is charged almost to the 15 volts. It has no bleeder resistor. I'm going to now discharge the capacitor. Ooh, that was a good one. This AC adapter has a center tap transformer, a full wave rectifier, a filter capacitor, a linear voltage regulator, and a bypass capacitor. The full wave rectifier only uses 2 diodes, but it does need a center tap transformer. The 4-pin voltage regulator needs several volts between the input and the output, and that is the major factor in wasting power. This 4th pin is an on-off gate, though it's left floating and not used in this design.